Hey everybody, this is Mr. Walsh coming at you talking about Lab 24, hydrolysis of salts and the pH of a buffer solution. Now, let's talk about the write-up for the second half of this lab, Part B, where we make a buffer solution, and for this, in this case, we have a buffer solution of the weak acid HC2H3O2, which we call acetic acid, and its salt, Na, or sodium, C2H3O2 acetate. So, just a quick thing, remember that a weak component and its conjugate makes a buffer. So when you take acetic acid and mix it with sodium acetate, that's going to be a buffer. And so then in the lab, we were asked to figure out the pH of the buffer, or we were actually going to measure the pH of the buffer, measure the pH of HCl, and then measure the pH of the buffer plus NaOH. And so these calculations can be pretty difficult. And this is what makes this part of chemistry probably more difficult than others, is because not only do you have to know the concepts, but you also have to be able to do the math required. And there's a lot of that goes on here. So I thought that I would go over some of the calculations using kind of sample data, sample numbers, and then we can go from there. So let's get into it. So this first one is just the buffer. So the buffer is a mixture of the acid with the sodium acetate. And I would always suggest anytime you do these problems, whether you're doing it in the lab or whether you're doing it as part of the class, I would definitely write a reaction. And so the acid equilibrium reaction, which is what we use for just a buffer, is going to be the acid HC2H3O2 plus H2O is in equilibrium with H3O plus C2H3O2 minus. Okay, and I left my states off of there because that's just what I'm going to do. And I'm going to move my calculator just around, I guess. There's no convenient place to put it. The reason why I like using the reaction is because now what I can do is I can do my ICE chart where I have the values, and I can put my ICE chart together, and I know what I need to be able to get to the end value. You know, it kind of uses this as a guide. So let's assume, and I know that that's a strong word, but the lab says that we probably want to use about 3.5 grams of sodium acetate. So let's just say that we added 3.50 grams of sodium acetate. That just makes life easier for the purposes of the demonstration. Now you should use whatever value you put here, and that's going to change slightly your calculations. And this is how I'm going to know if you did the lab. I don't want to say correctly, but if you did the math related to the lab correctly, it's because I'll be able to see what you put in for that value right here. Okay, and so remember that when we do these ICE charts, the units of the equilibrium ICE part is in molarity. Okay, so if we're going to do this in molarity, we need to know what the molarity of the acetic acid is, and we need to know what the molarity of the acetate ion is. We don't care about water. Water doesn't contribute, and then we don't have any of this to begin with. So we really just have to figure this out, and then once we get that, then we can solve. And that, I'm not saying that that's easy, I'm just saying that's what we need to do. So this is actually, this box here is a little easier than maybe this box, so we can start there. So 3.5 grams of sodium acetate is how much I'm saying we added. Again, you're going to write however many you think, or not that you think, but that you did add. And now I'm going to have to convert that to to moles, because we use molarity in here, and molarity is moles of solute per liters of solvent. So 3.5 grams. Grams goes on the bottom. I use this as an X line. That's how we convert. Okay, and then moles. And in the lab, this lab gives us the formula weight here in grams per mole right there. So it's 136 grams for every 1 mole. Okay, and now we turn on our calculator and we do 3.5 divided by 136, and we get an answer of 0.0257 moles. That's not volume though. Okay, so volume, remember, we're using, let's see, I think it was 8.8 milliliters of the acid, right? I'm looking it up right now. Yep, so it's 8.8 milliliters of acid, and then 55 milliliters, 55.6 milliliters of water to give a total of, let's see, 8.8 plus 55.6. That gives us 64.4 milliliters of total solution. Okay. So here we have moles, and so we're going to take this and we're going to divide this by the liters that we just calculated, or milliliters, 0.0644, and that's going to give us the concentration of the acetate. So we have 0.0257 divided by 0.0644, and when we get that, we get, okay. So that's kind of a good one. So that's 0.399. Okay? I sniff a lot when I make these videos. I don't know why. Okay. Excuse me. So now what we're going to do is we're going to calculate the initial volume of the acetic acid. Now to get that volume, that's going to be a little bit different, because here we started with an initial concentration that was 3 molar. But then we took that and we diluted it by a whole bunch. So when we do a dilution, we have to use M1V1 equals M2V2, or MAVA equals MBVB. Okay, but whatever, it's still the same. It's the same idea that the beginning stuff here is going to, when multiplied, be equal to the ending stuff there. And so the initial concentration of acetic acid was 3.0 molar. And then the initial volume of that, I think we added, it was 8.8 milliliters. And that's going to equal whatever the new molarity is times the new volume, and that new volume is 64.4. So we're going to take 3. We're going to go 3 times 8.8, and then we're going to divide it by 64.4, and that's going to give us a concentration of 410, okay, molar. So that means the initial molarity of acetic acid is 0.410 molar. At this point, this should give us an ICE chart that we can solve, just like the ones that we would normally do in class. So we're going to go minus x plus x plus x, and this is going to be 0.410 minus x, and this is going to be x, and this is going to be 0.399 plus x. And we can either use the Henderson-Hasselbalch equation, or excuse me, or we can just do the ICE chart. I always suggest doing the ICE chart because the Henderson-Hasselbalch equation is just a rewrite of that ICE chart. And so this ends up being Ka is equal to products, which is H3O plus, times the concentration of the conjugate base, which is acetate ion, all over the concentration of the acid. Okay, so now we plug in. So this ends up going to, let's see, Ka for acetic acid is 1.8 times 10 to the minus 5. And that equals H2O, which we don't know, which is X. And then this, I just want to scroll up to make sure that I have the right value. Okay, so it's 0.399 plus X over 0.410 minus X. And when we do that, we can use the 5% rule. And the 5% rule allows us to cross off both of these. And now we can do the math to solve for X. So I'm going to do 0.399 divided by 0.410. Okay, and then I'm going to do 1.8 times 10 to the minus 5. And then we're going to have to divide that by the answer. Okay, and so now that is equal to about 1.85 times 10 to the minus 5 is equal to X. We're not quite done there because that is just the concentration, and the problem asked for us to calculate the pH. So we have to take the negative log of that, and when we take the negative log of that, we get a pH of about 7 point. Read it, Walsh. It says 4.73. Okay, and that's the pH equals the pH of the buffer solution. Okay, that's all fine and dandy. But now the second part of this says that you want to calculate the pH of the buffer solution after we've added the HCl. Now, the point of the buffer solution is going to keep the pH of everything, is going to keep everything right around whatever the initial initial pH of the buffer solution was. And that initial pH is 4.74 or 4.73. Okay, and so what we want to do is recalculate now. If we add, let's see, I think it's 1 milliliter of the buffer solution. Okay, so we also have to keep in mind that the setup is a little bit different. So in the first part, we had our 64.4 milliliters, and we were asked to take that and split it and use half of it, 32 milliliters, for this half, and then 32 milliliters for this half. Okay, you could split it completely in half here and say 32.2 if you want. Okay. And then we do it. So that's going to change a little bit what we're doing. So let's do this based on what's going on in the problem. Now, I'm not going to say that this is easy. I'm not going to say that this is the only way that there is to do to solve these problems. But with the way that I teach the class, I think that what you need to see is that it's a buffer here, and then we're going to add something to the buffer, and so that triggers a certain way to solve these problems. And when we do that, the way that we solve it is we do a stoichiometry step first, followed by an equilibrium step, and then we can go from there. Okay, so the stoichiometry step for this reaction, let's see, in order to do this, we're going to have to figure out what's in solution and what's reacting. I'm going to get rid of the calculator just for now. Okay, and now I'm going to go and I'm going to say what's in the solution, because we need to write a reaction for the stoichiometry step. So we're going to have HCl, the strong acid. We have HC2H3O2, the weak acid. And then don't forget we have the buffer, the thing that makes it the buffer, which is the salt of that weak acid. So now we know that the HCl is going to do something. Well, this is an acid. Let me color code that. That's an acid. And we know that acids are going to react with what? Yeah, bases. So is this a base or is this a base? Well, this is an acid. It's HC2H3O2. You can tell it has the H out front. That's Arrhenius theory. And so this is the base. So these two things are going to react with each other in the stoichiometry step. So when we write, I always have a hard time saying this, when we write a reaction, not write a reaction, okay, when we write a reaction for this, the reaction is going to be the acid, the strong acid, okay, I'll do it this way, plus the base, NaC2H3O2, reacts to form, it's not in equilibrium, HC2H3O2 plus NaCl. Now I'm going to take this one step further, and I'm going to erase the Cl and the Na, and then this guy, because you know why? All of those are spectator ions. Okay, again, it's a lot of stuff to remember. Okay, so that's stuff from like a long time ago. So if they're spectator ions, they don't play a part in the reaction. They just sit around and make everything kind of look good. So this is the reaction. But the stoichiometry reaction, make sure that I'm clear about which step this is. The stoichiometry reaction, that needs to be done in moles. So we need to figure out how many moles of H plus we added from the HCl. We need to know how many moles of sodium acetate, how many moles of acetate there were in the reaction, and how many moles of the acid there were at the beginning. Okay, so there's a couple of ways to do this, but I prefer to do this kind of the more chemically appropriate way. Okay, of course you could go back here and you could say, well, we started with so many moles from here, and cut that in half. Okay, I'm not necessarily a fan of that, only because in the lab, what we did is we took that buffer, which happens to be pre-made this time, but it doesn't necessarily have to be pre-made in the future, and we split it in half and used the two halves. So we have concentrations, and we can take those concentrations and figure out how many moles of each thing there are to begin with here. Okay, so we're going to go and we're going to say, we're going to go back here and we're going to say, well, the original concentrations is 0.399 and 0.410. Okay, this was, let's see, 0.399 molar acetate. There's a 0 in front of that. And 0.410 molar acid, HC2H3O2. Let me double check, make sure that's right. I always double check this. Okay, so acetate and then acid. Okay, acetate, acid. Okay, but now keep in mind that, again, just like the last time, we're doing a dilution. A what? A dilution, because we didn't just have 32.2 milliliters of this, then we added 1 milliliter of HCl, so we actually have a total of 33.2 milliliters. Stuff from even before here. So I'm going to take this and we're not going to do this part of the problem here. Okay, but so let's come back here. How many moles? So for the A minus, for the C2H3O2 minus, and we have 32.2 milliliters, and that's going to be, that equals to 0.0322 liters. We're going to X-line that. Now when we X-line that, because again we want to do this in moles, we're going to have, let's see, 0.399. Remember, molarity is the same as saying moles per liter. So now, maybe I can bring my calculator back, and I can go and I can turn it on, and I can say, what's 0.0322 times 0.399? And that's going to give us the number of moles in this for the acetate. And so that is 0.128 moles. And I'm not even going to put the unit there because I know that stoichiometry always is going to use moles. Now I'm going to do the same thing for the acid, for the weak acid. It's 3O2. And so again, we have 32.2 mil. And the whole reason why we're doing this is because we did a dilution, and so when we're adding stuff, we can't keep the molarity. We have to do these things in moles. That's the whole reason we're doing the stoichiometry step in moles. And so that equals 0.0322 liters. We're going to multiply that, and we're going to, again, we X-line that, and that's 0.410 moles for every 1 liter. Okay, so now we're going to do the same sort of math. 0.0322 moles times 0.410 liters, or moles per liter. And so now we started with 0.0, helps if I write this number correctly. You guys out in the audience here are probably like, you miswrote that number! Okay, but I caught myself. Okay, that number there I rewrote. Okay, and so let's see, 132. Okay, so and now we need to know how many moles of H plus we had. Well, for strong acids, we had 1 milliliter of 6 molar HCl. Okay, so that's 0.001 liter times 6 moles for every 1 liter. Now this one's the math is a little easier on here, 0.006. So because this is a stoichiometry ICE chart, we have to know which one's the limiting reactant. The limiting reactant is this guy because it's the one present in the least amount. So this is going to be minus 0.006, and that's going to leave us with nothing left. And right here, 22 and 3/4 minutes into this video, we get to the real reason why buffers work. This is why I love showing the chemistry, showing the math behind the chemistry, is because a buffer resists change in pH. Well, how does it do it? Well, it does that because it chews away, it gets rid of, it reacts away the strong acid, which is the chemical component that controls the pH when it's there. So if there's no strong acid in the solution, now we're just reverted back to being controlled by how much weak acid and its conjugate is there. And so that's why I love showing this, is because here we have a strong acid, and when we do this, it's used up completely just by being present with the buffer. That's how a buffer buffs. Is that what a buffer does? It buffs, but whatever. Notice that it's 0. Okay, so we're going to do the same thing for each of these. Minus 0.006. This is plus 0.006. Okay, and so now we're going to subtract this. This is 0.0068, and this is 0.0192. Okay, so now we have the number of moles. But that doesn't get us to the pH, because what we can do from there is now we can take this, and now we can do our equilibrium step. Our equilibrium step now shows us how it goes back to the acid-base reaction, where we take the weak acid, acetic acid, plus water. Now that is in equilibrium with the hydronium ion plus C2H3O2 minus. And this now will get us to the pH of that solution, because that's how we figure out the pH of a weak solution, is by doing equilibrium. but we have to use the amount present here. Now this is in moles. Equilibrium is always done in, let's see, molarity. So now we have to go back and we have to convert from moles that we did on this ICE chart into molarity that we did on this ICE chart so that we can actually solve the problem. How many moles of this do we have? That. But then how many liters do we have? Okay, well, let's go here. Let me do this here. Okay, ICE. ICE. I have heard people call it a side chart or a side table. That's where start, what is it? Start, subtract, I don't know. In addition or subtract, I don't know. And then difference, that's what it is. D is difference and E is end. But I use ICE, initial change equilibrium. And then, let's see, for HC2H3O2, the initial concentration of this is, okay, well, that's how many moles we have. 0.0192 moles. How many liters do we have? 0.0332. Remember, we had the 32.2, half of the original buffer, plus the 1 milliliter is 33.2 milliliters, which is that number there. So that concentration is going to be 0.0192 divided by 0.0332, and that, the concentration, the initial concentration of this is 0.578 molar. Again, I'm not going to put the units there because I already know that equilibrium ICE charts are in molarity. Okay, so now for the acetate, we have 0.0, so this is C2H3O2, and this is 0.0068 moles. And again, it was in a 33.2 milliliter solution. I guess I make my units right. That should be milliliters. It was 33.2 milliliters, so this should be in liters, not milliliters. Okay. Hopefully you caught on. Okay, and so now we go 0.0068 divided by 0.0332. And this gives us a concentration of 205 molarity. Now look at what the difference is between this and just the buffer alone. Just the buffer alone had a ratio of about 1 to 1. This and this were in a ratio of 1 to 1. Here, chemically speaking, the ratio has changed because we reacted away all the acid with the base. So this acid is gone, this base is gone. So that means there's more acid in the solution to equilibrate. I always don't know what the verb form of equilibrium is. But now there's more acid here. This ratio is not 1 to 1. It's like 2.5 to 1. And so that's what changes our initial pH. And so now, because there's so much more acid here, our pH should be below what the pH of the plain old buffer solution is. It's not necessarily just a simple fact of, oh, we added acid to it, so the acid is just going to bring the pH down. It does, but there's more subtle things going on than just the acid brings the pH down. Okay, it's not the strong acid. In reality, it's that we have changed the ratio of the weak acid to the weak component. There's some really neat chemistry going on here. Okay, again, this is what makes this really hard to get. Okay, not an easy thing, but elegant. There's an elegance to it. Okay, especially after you've been watching this for 29 minutes and 40 seconds. Okay, so this is 0, none of that. Water doesn't matter, liquids don't play a role. And so this is going to be, let's see here, minus x plus x plus x. and we go 0.578 minus x, x, and 0.205 plus x. And so now we can do our, use our equilibrium expression. Okay, 1.8 times 10 to the minus 5 equals the products, which is x times 0.205 plus x over 0.5, I forgot what it was, 578, I guess I could have looked at my calculator, 578 minus x, solve for x. Now we can shortcut it. These can cancel out because of the 5% rule. So now we can go 0.205 divided by 0.578. Now we take that and we do 1.8 times 10 to the minus 5 divided by that. Okay, and we get 5.08 times 10 to the minus 5th is equal to x, which is also the concentration of the hydronium ion. Now, that's not what we were asked for. We were asked for the pH. And remember, the pH is equal to the negative log of the concentration of the hydronium ion. Whew. Okay. So what do we do from there? Okay, we do negative log of the concentration of the hydronium ion, which is what we have previous. We get an answer, we get a pH of about 4.29. Okay, and that's exactly what we expected. We add an acid, the pH is going to go down. Okay, so your job, using these as kind of the model, you can answer this question right here that I crossed off, hopefully doing this with the sodium hydroxide. Starting way back up here, you have to list the stuff. Instead of HCl, we have NaOH. NaOH isn't going to react with the base because it's already a base. It's going to react with the acid. So you have to write a reaction of the base plus the acid, giving you something. Okay, and then converting everything to moles, finding out how many moles of everything are left. Once you have the moles of everything that are left, then you can do the equilibrium and solve the equilibrium and go down here and figure out what x is. And then, at the end, you're going to compare those values. So, take the video, look at what I've done, model that, pause, rewind, fast forward, stop, and hopefully this is going to help you write up this lab and understand what's going on in a buffer solution. Have a great day.